Welcome to Lecture 1.2. In this lecture, I'll be covering signals in NMR and what it means to be a group of equivalent hydrogens. As I mentioned in our last lecture, in this NMR spectrum, we have three different signals labeled A, B, and C, and each one is to represent a group of equivalent hydrogens. So the chemical formula for this chemical is C2H6O. And while it won't always be the case, as we'll discuss, you'll notice that the total number of hydrogens in the molecule, which is 6, is equal to the sum of all the total integrations. When that happens, that is evidence to us that this number is in fact the number of hydrogens represented by the signal. So having one hydrogen be a signal that's distinct maybe makes sense, but how can you have three hydrogens that are the same, that are equivalent, that represent the same signal? That seems confusing. Let's break that down, and I think the best way to do that is to go through some examples. So hydrogens can be equivalent by one of two processes, either rotation or symmetry. Starting with our first molecule here, let's draw in all of the hydrogens just to be thorough. We have 2 hydrogens on this carbon and 3 on this carbon. So essentially, equivalent hydrogens need to be arguably the same. Looking at this hydrogen, it seems to be unique in this molecule. It's the only hydrogen that's directly connected to oxygen. And really, if there's no way that you can define a difference, it's got to be a unique hydrogen. So we'll call this one signal. And if I had to ask the integration of that signal, or if you had to guess what that integration would be, we could maybe call this HA and give it an integration of 1, as it is a group of hydrogens, right? It's a pretty lonely group. It only has HA in it, a single hydrogen. Jumping over to the left side of the molecule, though, what's interesting is that despite there being 3 distinct hydrogens, all 3 of them are going to be the same. They're going to be equivalent. Now, if time was frozen and this molecule was static as if it is on the page, it would appear that these are a little different, that this HB is closer to this oxygen, or that hydroxyl group, than this one is. So how does that make any sense? The way I like to view it is that, of course, this molecule is never going to be frozen unless it's at absolute 0, and that this carbon, being an sp3 carbon, is totally able to rotate. And much like how a tire moving slowly, you can see the individual spokes. When that tire starts moving quickly, all those spokes really just blend together. They all look the same. That's because our eye has a refresh rate, right? When we see a tire moving, our brain takes pictures and it tries to put them together in video, and that's how I view pretty similar to what the NMR machine is doing. Since these 3 hydrogens are rotating so quickly, the NMR machine doesn't really detect a difference. On average, they're all the same. So with that in mind, as a general rule, with many exceptions, as we'll talk about, hydrogens that are connected to the same carbon and that are able to rotate are very likely to be equivalent hydrogens. So here we have a 3 integration signal, as there are 3 hydrogens in that group. And following that same trend, since these 2 hydrogens are connected to the same carbon, we would expect them to be similar by rotation as well. That would be an integration of 2 signal. Great, so that was a simple molecule, ethanol, and who doesn't like ethanol? But let's move on to a little bit more of a challenging one. Let's go down here. So in this molecule, let's quickly draw in all the hydrogens. Now take a second, maybe pause the video if you want, and try to guess how many unique groups of hydrogens, or another way to phrase that is how many signals would we expect to see on the NMR spectrum of this molecule. If you got your answer, let's take a look. So let's start from the right side here. These 2 hydrogens would be expected to be the same, as they're connected to the same carbon and are able to rotate. They would be expected to have an integration of 2. just to be clear, the fact that they're labeled as A doesn't really matter. You can label them whatever you want as long as those two are labeled the same. Same goes for these two hydrogens. They're on the same carbon and they're able to rotate. Now, this hydrogen over here, the one that's by itself, is clearly unique. It's the only hydrogen on that carbon, and we're going to give that an integration of 1, as that group of hydrogens represents one single hydrogen. But where many students are going to make a mistake here is that all 6 of these hydrogens are actually the same signal. They can all be labeled HD. And in total, we would expect an integration value of 6, as there are 6 hydrogens represented by that signal. Now, the reason why they're the same is because of rotation. This carbon, being sp3, is able to rotate. And so there's no reason that these 3 hydrogens and these 3 hydrogens can't spin around. And for the same reason that these 3 hydrogens were identical, these 6 will be identical as well. So in total, we would expect 4 signals for this molecule. Moving on to our third example, let's take a look at how symmetry can affect things. Remember that these groups can be equivalent, or these hydrogens can be equivalent, by either rotation or symmetry. So far, we've only covered rotation. So in this molecule, diethyl ether, we can see that there's a total of 5 hydrogens on the left side of the oxygen and 5 on the right. Here you'll notice that there is a total plane of symmetry across the molecule. That is, the left side is identical to the right side. If you were to flip it over, you wouldn't change it. So it would make a lot of sense that these 3 hydrogens would be the same due to rotation, and that these 2 would be the same due to rotation, an integration of 3 and 2 respectively. However, these would also be HA, and these would also be HB. As we'll discuss, the integration values that you generally get from a molecule with total internal symmetry can be somewhat misleading. However, for now, we can say that because of symmetry, these 2 hydrogens are chemically equivalent. That is to say that there's no real chemical difference between them and the ones on the left and right. For that reason, we may expect to see a total integration for HB of 4 and an integration for HA of 6. That's how symmetry can make hydrogens that are quite far apart, right? These are, 5 bonds apart. They are still chemically equivalent. And that's an important thing to catch when you're dealing with NMR spectra. Let's take it up one last notch and introduce a benzene. Feel free to pause the video and try to find out how many signals we would expect to find in this molecule. Good. Hopefully you have an answer in your head. Let's take a look through it. So just like we saw before with that last hydroxyl group, this hydrogen here is clearly unique, and we would expect to see an integration 1 signal representing it. However, on the benzene, we have 4 different hydrogens. Now what's going to be interesting here is that the hydrogen on the left and the right are going to be the same. However, these ones below are going to be different than the ones on top. So it might make sense that these are different signals. After all, HB is closer to the hydroxyl group than HC is. Alternatively, HC is closer to this substituent than HB is. They're different. And if they're different, we're going to call them different signals. However, why are these 2 the same? Right? The answer is symmetry. This molecule is symmetrical, although this part doesn't look symmetrical. Remember that this can rotate. It's not really a factor, right? At the end of the day, try to justify any difference between these 2 hydrogens. Convince yourself that there's a difference, and it's very hard to. Right? This HB is, 3 bonds away from that oxygen. So is this one. It's 1 away from HC. So is this one. They're very similar, and the NMR machine won't be able to tell the difference. We would expect both of these then to have integrations of 2, both for signal B and signal C. Then we have our 2 hydrogens here. They would be similar or equivalent hydrogens due to being connected to the same carbon. And last but not least, very interesting ones. We have 9 hydrogens here that are all going to be equivalent. We call these He with an integration of 9. Why are they all equivalent? You may have picked up on it by now, but notice that they're all connected to the same sp3 carbon, and they're all able to rotate. I find these 4 examples to be very informative in terms of seeing how equivalent hydrogens are generated by either rotation, as we've seen, or symmetry. With that in mind, let's talk about a couple quick exceptions. I briefly mentioned that hydrogens that were sharing a carbon were equivalent. This is generally true for simple spectra. However, it's a bad rule to follow, as there are exceptions to that. There are more than 2 exceptions, but here are 2 very notable ones that I wanted to bring up, as they share a common trend, the idea of restricted rotation. Let's take a look at this molecule, the idea of geminal alkene hydrogens. Here, we have 2 hydrogens that are on the same carbon. However, they are different. They are not the same. Now, if this was a single bond, that carbon would be able to rotate, and these hydrogens would be equivalent. Remember, however, that a pi bond cannot rotate. With that in mind, notice that HA has a cis relationship to an oxygen, right, the hydroxyl group, where HB has a trans relationship to it. Well, not entirely different. It's different enough that these are going to appear as different signals on the NMR spectrum, and they're going to lead to some complexity, as you'll see later in this section. So that's one example of how restricted rotation can lead to 2 hydrogens being different while sharing the same carbon. Another example is in rings. So I say here cycloalkane rings. In both of these cases, notice that there is a total plane of symmetry. So this HA that's on a wedge would be expected to be similar to this HA due to that symmetry. Notice that they're both on wedges, which means that they're cis to the bromines on that ring. That makes them different to the ones that are underneath the plane on dashes, HB. Right? If those carbons could rotate, HA and HB could become equivalent. However, cycloalkane rings are not able to rotate like that. Once again, we see this situation where we have a single carbon that has 2 different hydrogens on it, 2 different equivalent groups, 2 different signals we would expect to see in NMR. With that in mind, now we have a better understanding of what these individual signals represent, and as well a bit of information on the integration. We can now move on to really breaking down the 3 different pieces of each signal, starting with the x-axis location or the chemical shift. I'll see you there.